is the founder and chief scientist of Cloudera. Before that was the chief entrepreneur for Accel. And before that was the, he conceived, built, and led the data team at Facebook over the last several years. And he has certainly been driving statistical applications and machine learning in big data areas. And we're looking forward to hearing whatever he has to say to us today. Thank you, Jeff, for agreeing to come down and talk to us, and welcome.
All right, thank you for having me. I'm going to pop this into full page. Where is it? I haven't used a Windows computer in years and years and years. All right, cool. So I'm going to talk a little bit at a high level about some emerging standards for collecting, managing, and analyzing very large data sets, taking some paradigms that emerged in web properties and have been sort of infecting other industries and are slowly making their way into medical data. I'll talk about kind of the philosophy behind this new software, how it's been instantiated in software, and then give you some examples of how we've seen the software that I'm involved with applied to medical data. I think it's still very early days, and I'm trying to restrict the range of speculation to just the examples that I've seen and the software that I'm most familiar with. But I think there's a lot more to be said here. Okay, so at a high level, what's the philosophy behind the software that we build? Well, I think that one of the cleanest statements of what happens in data analysis, reporting, data mining, came from a book, one of my favorite books, Exploratory Data Mining and Data Cleaning. So they have a very terse statement of the problems. They say the true challenges in the task of data mining are, number one, creating a data set with relevant and accurate information. And number two, determining the appropriate analysis techniques to apply to that data set. So my philosophy for the first problem of essentially getting the correct data set available to apply your algorithms towards is, number one, to store all of your data in one place. So I've been informed that actually Zach Ives is talking after me, and I'm pretty sure he's going to talk about the other philosophy of letting the data live wherever it should live and sort of dynamically materializing it as needed. So I tend to think that it's much easier to just materialize it all in one place and go to town. Then again, I usually think from the perspective of a single organization rather than the perspective of many communicating organizations. Similarly, I tend to believe that single data centers are good enough to do your data analysis, and I think that the grid movement is very powerful, but also very complex and really difficult to use. So I think of a single data center and a single namespace for all your data. So that's the philosophy behind a lot of the software that we've built over the past several years, and a few corollaries from that sort of key thesis statement is store your data first and figure out the questions you want to ask about it later. I see a lot of projects blocking on what data to actually record before, so they block on actually recording data by attempting to decide the questions they want to ask of that data up front. And I believe that's an ineffective way to go about things. You very regularly come up with the questions you want to ask of the data after the time at which that data was generated. And if you chose not to store that data, then you're not going to be able to ask those questions of your data. So that's sort of my first piece of advice to anyone I talk to about how do we get started on this project. You know, we've been talking to SAS. They've got this sweet new algorithm for massively multidimensional linear regression, and we're pretty sure we want to use that algorithm. And the first question I ask is, well, what data have you started collecting? And they're usually, well, we'll get to that later. And that's kind of a problem because data is sort of the intermediate representation of science, right? You can't do science until you've somehow like transformed the world into bits. So figure out the questions you want to ask later, and guess what? You're going to probably evolve new questions as you start doing the analysis, and you're going to be pretty happy if you have sort of the adjacent data recorded to start answering some of those questions that you evolve midway through the analysis. So that's one sort of corollary to the philosophy of putting all your data in one place, so it's sort of put all of your data in one place. And the second is to store first and structure later. So even after you've decided that you want to record a specific piece of information, I see a lot of people block on, okay, let's go then perform a complex data modeling exercise. And this is very, if you've ever done any data warehousing exercises, this is really classic, right? You buy some book on dimensional modeling, you figure out what your facts and dimensions are, and meanwhile, the world is proceeding and you're not recording data because you're blocking on figuring out the structure for that data. So I think and a lot of that is because the systems that we've built, the software artifacts that we have to sort of cast our net through the world of bits, are very sort of opinionated about the way in which data should be structured before they'll store it for you. And so I think that we've done a lot of work to evolve software systems which are relatively agnostic to the structure of data. So I think those are just core pieces of our philosophy. Not everyone agrees with this, so if you don't agree with this, you're probably not going to want to use our software. But this is when I sat down to think about the data problem at Facebook, and since then when I've sat down to think about the data problem at our customers at Cloudera, this is kind of the starting point. So, if you don't agree with me here, we can part ways and, no hard feelings. But so some reasons why this is core to my philosophy. Number one, raw storage today is just so cheap. I think this is, I constantly hear people say like, but that'll result in 3 copies of our data. And I'm just like, okay, so the incremental cost to you is just so minimal. There's just an article today where IBM's tooting their horn about building this 120 petabyte data store, saying it's the largest data store ever in the history of the world. And, first of all, it's completely false. There's much larger ones inside of organizations that IBM does not touch. But second of all, the amount that's going to cost is about $4 million. And I can tell you today that, I've seen, in terms of raw storage, a little more than $4 million to get 120 petabytes at today's prices. And in fact, if you buy in bulk, you can probably knock even more off of that. And I'm pretty sure that IBM Global Services bill is going to run much higher than $4 million. In fact, I see people building tens of gigabytes, tens of terabytes data warehouses and forking over tens of millions of dollars to data warehousing providers for software alone. So it's I think people have a warped sense of how much storage costs because companies like EMC and Teradata have just been bending them over for the last several years. So, but if you just go do a search on Google for a hard drive and then do the math, this is about how much it costs. So I found, this is conservative actually. I can find you a 2 terabyte drive for $60 if I try really hard. But I counted a 2 terabyte hard drive to be $80 right now. So that's 4 cents a gig. You should really be able to store it. It's super cheap to store data, so just go ahead and store it. The distributed file system that I work with most of all, the Hadoop distributed file system, I've seen single instances larger than 50 petabytes. So this sort of supports the putting all of your data in one place. If you can scale your file system to greater than 50 petabytes, I'm guessing that most organizations have less than this data, then you can put it all in one place. And this limitation is constantly being raised, by the way. So I suspect that this will be greater than 100 petabytes if I were to give this talk next year. So you really, in terms of cost and in terms of the software capabilities, we're really able to put your data all in one place today. The philosophy, or the architectural reasons behind that, or the ideas behind it, is number one, use commodity hardware to build this out rather than going and buying some sort of gold-plated SAN array from someone like EMC. Use open source software, so rather than depending on these vendors to sit in their back rooms and patent all this stuff and then extract rent from you with their closed source software, go ahead and put it out in the community using open source software. Horizontal scalability, so building to scale in a horizontal fashion. So that incrementally adding new capacity is easy to do, and modular composable software components. So if you have a certain type of analysis or a certain type of data that you don't plan on storing, then hopefully your system shouldn't require you to install everything, right? So if you go and buy most commercial relational databases today, you're just getting this opaque blob of massive features that massive sets of features, most of which you'll never ever use or even turn to that page in the manual. So that's sort of the core philosophy for the first part of this challenge. So creating a data set with the relevant and accurate information. Store it all, worry about deciding what to store and how to structure it later, and then when the time comes to perform the analysis task, hopefully you've got a nice set of tools to create structure in that data. in terms of determining the appropriate, so the second problem of determining the appropriate analysis techniques, to borrow a phrase from Jim Gray, I think it's important to let everyone party on the data. So, traditionally, when you build a data warehouse, the only people who have access to the data warehouse are the business analysts, and then the data warehouse itself, as a software artifact, instantiates a limited set of ways to access data. So you're usually restricted to something like SQL, and then something like some procedural language that someone dreamed up in the 80s and has continued to bludgeon you with. So in Oracle, this is PL SQL, in Microsoft, it's T-SQL, et cetera. And you might even be lucky enough, if you're trying to load or export data, to encounter such arcane dialects of code as SQL asterisk loader. So there's actually an asterisk in the official trade name of Oracle's data import and export language. So this is, being handed these sort of arcane, very specific languages restricts the number of people who can actually party on the data. So one of the philosophies behind the software that we've built is to really identify the target end user for the analysis, and then build tools to facilitate that person's analysis. So if you're a developer, you speak a certain set of languages, right? You probably know how to code in something like Java or C++ or C for your systems work, something like Ruby, Perl, or Python for your scripting work, and then something like R or SAS for your data analysis work. So let's build interfaces which integrate with those languages and make it easy to do analysis for developers. If you're an analyst, you probably speak something like SQL, so let's build you this higher level query interface. Or you might prefer some sort of point and click interface if you're a business user. So let's build a graphical user interface. But let's ensure that we have a variety of interfaces for a variety of users, and that these are, they begin with the needs of those users first, rather than the capabilities of our software first. To enable everyone to be able to party on the data in the same data store, you need a few sort of architectural principles. You need to get these things right. Number one, you need to be able to isolate users from one another. So you can't have, it's kind of like if someone's throwing a party next door, you want soundproof walls because you want to play your music, not their music, kind of thing. So the same thing happens in a large cluster. If you guys have ever had a large Hadoop cluster used by multiple lines of business, you probably have the experience of someone running some monster query which takes down the whole system for everyone. So improving the isolation of the software is important, and that leads right into unified resource and workload management. So you want a single workload manager for the entire cluster. So once you've figured out how to isolate people, now you need to figure out how to divide up the resources of your cluster amongst those people. So really getting that workload management right and doing it in a unified fashion, so that all the different execution environments are happening within that one workload management system is very important. So as I mentioned, the execution frameworks, you don't want to just enable people to do, directed acyclic graph data flow programming. You don't want to just enable MapReduce. You don't want to just enable MPI. You want multiple kinds of parallel execution primitives to be accessible to your end users. Similarly, you want multiple interfaces to access those execution primitives for your end users. So you don't want to just enable them to do MapReduce in Java. You want them to be able to do it across multiple languages. You don't want them to just be able to write SQL. You might also want them to be able to write, something like Piglac. So there should be multiple interfaces to these execution environments. And then most importantly, I think these systems should improve over time. So there's all sorts of behavioral metadata generated when people do analysis, and you should be able to capture that and use it to improve their experience of the system over time. So just to give a visual representation of those bullet points, I think this is sort of a standard model in doing data analysis today. I don't know how familiar it looks to everyone here, but it's usually the case that you have some application database that's serving application requests often to a mobile or a web front end, and then someone comes along and says, hey, we want to analyze what's happening with this application. So they stand up some data warehouse, which is almost always a relational database. They set up some ETL process to move data from the application database into the data warehouse, and then they plug in business intelligence and analytics tools to do analysis over it. So what we're trying to argue for is a slightly different, is a little bit of a modulation of the architecture. So And so rather than just trying to perform ETL from the application database into the data warehouse, you might have a variety of application databases and data warehouses which can feed this large unstructured data store called Hadoop. And then, as indicated by the documents and images and log files above, in addition to just the data from the application database, you can have all of these heterogeneous complex data types being pushed into your system. And you can do some business intelligence and analytics over the Hadoop data store there while pushing some of the structured aggregates into a data warehouse for more traditional analytics that you might perform. So that's the philosophy behind the software that we've been building over the past several years, and I think that you'll find that philosophy encoded in software within companies like Google, within Microsoft, within Yahoo, within Facebook, within LinkedIn, within Twitter. And because a lot of these philosophies have been encoded in open source software, you're starting to see this software architecture emerge outside of the web domain. So, at Cloudera, we have customers in financial services and government intelligence agencies. We have them in telco, and retail is a very big adopter, and oil and gas, and life sciences has actually been probably the slowest to move of those 7 industries. But so what does that platform look like? Well, before I get to kind of the software components, I think the substrate of that platform, as I discussed, you really begin with commodity servers. Some people might call these pizza boxes. These are usually 1 or 2 rack unit servers, which contain anywhere from 4 to 12 disks. And they might have, today 16 core CPUs with, anywhere from 12 to 24 gigs of RAM. And one way that the cost has been lowered even further on the commodity servers. So you used to be able to go to white box vendors like a Supermicro to get very low prices on these servers. But companies like Google started building their own servers because they realized there was still a tremendous amount of fat even in these commodity server vendors. So, and Facebook realized the same thing, but rather than being like Google and trying to hide that from the world, Facebook decided to say, hey, let's take our data center designs and let's put them into the world. And so they created something called the Open Compute Project. And this is there's been tremendous vendor interest. A lot of cloud providers are looking into working with them. A lot of other web properties and financial services companies showed up at the first Open Compute Summit. So this is essentially taking data center and server design, putting it into the world, and then allowing everyone to innovate and put their learnings into the world. And then there are, a set of parts manufacturers who will take those designs and actually allow you to buy the servers. So Open Compute, I think, is really the most promising project, which is lowering our cost in the commodity servers aspect of this platform. Obviously, on these servers, we need some sort of operating system running, and Linux is really the predominant open source operating system today. To then tell these operating systems what software they should have installed and what configuration parameters should be set in order to get ready for our software that we're going to put on them to turn this into an analytical data platform. Tools like Puppet and Chef and CF Engine and BCFG2 have become very popular for open source configuration management. So you've bought your servers, you've installed your operating system. Now you want to turn them into a big distributed analytical data platform. Puppet and Chef help you do that. And then to allow those servers to talk to one another and form consensus, there's a coordination service. Google has a system called Chubby. In the open source world, we have a system called Zookeeper, which is important. So this is kind of the substrate of hardware and software that you need to get ready to install this analytical data platform. So there's sort of 3 key components for the storage aspect of this analytical data platform. Distributed schemaless storage. So you'll remember that part of our philosophy was to store data first and then worry about structuring it later. So at the base, having something which is speaking, file system or block or object protocols, schemaless data storage is very important. In our world, we work with the Hadoop distributed file system, and that's evolving very rapidly. I'd say the most promising alternative to that I've come across is Ceph. So these are 2 options for doing sort of distributed schemaless storage at very large scale. So once you've got that schemaless storage, there's a subset of your data which you're going to want to actually bless with structure. So you might recognize there's some structure latent in that data. For example, a CSV might be a file, but in reality it's a set of rows and columns. So in order to work with data which is structured as rows and columns, there's kind of you want to optimize for two different workloads. One is sort of append only. So this is very common in the data warehousing world, right? Things like log files, our memory, for example. We would prefer to be append only rather than sort of read write, because we don't really want to forget experiences that have happened to us. And then you can make specific optimizations with append only table storage to enable faster analytics. So in our world, in the Hadoop world, we have tools like RC file to do columnar layout of append only tabular data. And then we want to keep around metadata about, which table is stored where, what type is that column, what is the cardinality of this column, et cetera. And in the Hadoop community, they've taken the Hive metastore and they've generalized that into a system called hcatalog. So that's great, but every once in a while you have data which you want to actually be mutable. You want to be able to update the rows and columns of that table, and HBase is our solution in the Hadoop world. It's modeled after Google's Big Table, and it's very widely deployed at very large scales these days. So this allows you to have sort of real-time, low-latency access to very, very large tabular data, and then go and create, read, update, and delete individual cells. So this is at our base. So we have infrastructure for doing schemaless storage at the tens of petabyte scale, and we now also have infrastructure for doing tabular data storage, which all runs within the same software system. These tools for append-only and mutable table storage are built on top of the distributed file system. And this is sort of speaking to the modular software components, part of our philosophy that I discussed. So that's great. We now have this giant gaping maw of bits, which we can hurdle data into at low cost and potentially give structure to it as we discover structure in that data. So now we want to actually go do work over that data. So I talked about wanting to have isolation and unified workload management. So this cluster resource management problem is being addressed in a variety of places. Two of the most promising directions are a system called Yarn that was constructed at Yahoo and a system called Mesos that they've built at Berkeley. So you can think of these as essentially a process scheduler for your cluster operating system. So once you have a process scheduler for your cluster operating system, you want processes that can run on it. So these sort of base distributed parallel processing frameworks, I think the most popular is MapReduce, but I think people have over-rotated a bit on MapReduce and have presumed that this is somehow the only way that you can do parallel processing of large volumes of data. But of course there are many others. In the high-performance community, they're quite familiar with MPI, message passing communication-intensive parallelism. Within Microsoft, they have a system called Dryad, which allows more expressive data flow than MapReduce. They also have, within Google, have tools for doing things like iterative bulk synchronous parallel computations like Pragle, and very fast scan and aggregation workloads, which are very common in analytical queries. There's a system called Dremel within Google. So having a variety of parallel processing frameworks which run on this cluster process scheduler enables a wider variety of analysis to be performed over your gaping maw of bits of data. Once you have these underlying execution substrates, you want to have high-level interfaces for your to allow everyone to party on that data. So for programmers, tools which actually integrate with their programming languages are very important. So Flume Java is an API for doing complex workflow processing over data stored within Google's data centers. And it's a Java API, and there's work to make an open source version of that. Dryad Link is a nice version that has been built at Microsoft. So Link stands for Language Integrated Query. And so this enables you to, within .NET languages, sort of iteratively construct complex queries to run on the Dryad execution substrate. Within the open source world, we have tools like Pig Latin, which is sort of a mix of declarative and procedural query construction primitives. HiveQL, which is really a dialect of SQL, which allows you to specify in a declarative fashion how you'd like to get your data back. And systems like Uzi, which are configuration-driven workflow engines, which allow the easy adaptation of graphical user interfaces and the ability to construct, multi-hundred stage workflows, which is very common in things like natural language processing. And then the last thing is you've got, the substrate of hardware and software infrastructure needed. You've got storage primitives and you've got parallel processing primitives. Now you need to integrate this with the rest of your data center. So for the first thing you're going to do is probably populate that system with data. So there are tools like Scoop and Apache Scoop and Apache Flume, which allow you to take data easily from relational databases and log files and import it into this analytical data platform. And then you probably want to be able to access the data in that once you've imported it it, you want to access that through traditional tools that you're used to using. So things like fuse bindings to enable you to mount file systems and access it as if it were a standard file system, as well as JDBC and ODBC drivers, which enable you to use a wide variety of query tools which work with JDBC and ODBC, can be powerful ways to get at this platform. So lastly, I want to review a few applications in the medical domain of this existing open source software infrastructure. One that we've done in my group at Cloudera, we have a small team of data scientists who work with sort of fringe projects and large data sets to kind of demonstrate the power of this platform. So we worked with the FDA to do some phase 4 post-market analysis of drug safety. It turns out their adverse event reporting system data is all available in the public domain. So we took a few terabytes of that data, we pushed it into a small cluster that we had sitting around, and rather than having to use any sort of complex sort of matching algorithms to figure out novel 3 and 4 drug combinations, which are producing surprising adverse drug events, we were able to use Pig to write a pretty brute force script to basically just combinatorially combine the different drugs that people were taking, and then have a filtering step where we worked over that combinatorial, that sort of outer product, to essentially filter it down to the ones which actually had some significance. So you could obviously design complex algorithms to identify these adverse events, but the fact is we were able to do this in less than a day with very little domain expertise, just poking and prodding through their public data set. And we were actually able to send to them 3 new sort of 3 drug combinations, which were producing a very statistically significant set of adverse drug events that hopefully can be used for hypothesis generation and then subsequent studies. Another one that I'm aware of that was actually done here at UCLA is the seqWare query engine. So the goal here is to load up thousands of genomes along with their associated variants and annotations and allow people to rapidly query. It runs on HBase, which is the mutable table store, which I described earlier. And it's actually all open source, so you can go download and play with that today. Another one in the medical field is working with imaging data. So they call this analytical pathology imaging. And so they augment Hive, which is our system for append-only table data, for querying with a SQL interface append-only table data. And so they augment Hive with spatial query capabilities and use this to do guided diagnosis of pathology images. And the work on that's being done at Emory University. One of our customers at Cloudera is a company called Explorith. These guys are based in the Midwest, so they're close to my heart. They're building a medical informatics platform with the goal to allow people to search and analyze patient populations, treatment protocols, clinical outcomes, and a variety of other data sets. So they're actually core contributors to the HBase project, the mutable table store that I discussed earlier, and it was used in the seqWare query engine. So they've an employee named Doug Mail who was recently named as a committer on that open source project. Another company that I'm familiar with in the Bay Area is a company called NextBio. They do what they call integrative genomics. So they've built a platform for integrating public and private information about sequence data. So they will crawl the web and crawl literature databases and pull out as much as they can about different genes and variants, and annotate the public information, and then they will allow you as an organization to combine that with what you know privately from your investigations. And they use Hadoop and related tools very heavily in their pipeline. Another one of our customers at Cloudera is a company called First Life Research, which does literature search over a lot of the medical literature. You may be familiar with, I was unable to find very much technical detail on how IBM Watson does automated diagnosis, but so the deep question answering technology developed at IBM that powered the Watson system, which was able to do some good work on Jeopardy very recently, has now been pointed at sort of automated diagnosis. This is a problem that has been tackled for decades, but it turns out, it seems that a lot of the techniques used by Watson, which is trawling over very large amounts of text data, is turning out to be very useful. A little bit further afield, there was a really interesting paper from Microsoft Research recently on the phenomenon of cyberchondria, where they were trying to essentially understand how web content related to symptoms and diseases was navigated by your typical web user, and compared that to how they would be diagnosed by a clinician. And so they took search logs and they did analysis over that. So this is a very common use case of our software. It did not use open source software. It used Microsoft analogs of that software. So that's the majority of the examples I wanted to talk to. And now I'm just kind of curious to hear from everybody in the audience how this might be used for your problems.